Okay, you can start now, Engineer Mohammed.
Okay, thank you very much. Thank you very much for everyone who joined us today in this webinar. I would like to welcome you all. I hope this webinar will take almost the marks we are going to discuss and present and get benefit of all of it. So our topic today about production problems and field monitoring. You know, the every field has its own characteristics and problems, and some problems are major, and some problems are very small. Uh, Even though, so we have to deal with each one. So we will review many of common problems in this webinar. So these problems might be for producing wells and might be for injection wells. And there should be information and about each problem. Who might be we need to consult in terms of diagnosis of this problem in that field or that well, specific well. How that problem can be remedied, because otherwise we will start losing the production from that well or the field in the field, and we will start losing money as well because it's cost effective. And the other thing, who we need to consult with, to set the strategic plan for remedying those problems. And in the end, there should be a plan on the ground. We have to put it and try to implement all these remedial actions. So reservoir monitoring, this is the start with the problem, the field problem. So there's many production problems. You know, it can't be recognized in early life in the field. And I mean, not the field and the well production rate, production life, or at late when we have it's become a major, and we can suffer from that problem unless we deal with it when it just started. So what we should do and how we can reduce that effect by monitoring well performance. So this is the essential parameter we have to keep in mind. It's monitoring of the well performance, field performance. Field performance, I'm sorry. So this is the essential part we have to keep in mind as we are petroleum engineers dealing with the field in terms of field management or well management. So this is the best chance to detect the problem in the early life, or when it's just happening. So mention that. So how we can do that? It's by doing a routine well monitoring. So a routine well monitoring, this kind of routine monitoring, we have to plan it beforehand and know what we need to know about our wells, about our field, our facilities, our pipelines. So, for example, let's consider this is this whole system. So starting from the reservoir to the wellbore to the Christmas tree, pipelines, chokes, surface facilities, etc. Then to the degassing station. All these we have some kind of problems we have seen, it can be happened. So each part need to be monitored well through a procedure. We can put it in hand. Should be a surveillance plan, should be any mitigation for any problem happened in any part of this production system. So these can be put in hand by putting in intervention opportunities. Otherwise, we can maybe lose some part of it when a problem can be happened. So, for example, when we have difficulties in determining downhole performance, that may cause and we don't have a forecast on for production of that well, and we don't have the right production rate for that well. Maybe some downhole pressure, it's not accurately calculated. For example, if we don't have sampling points, so if we need any data from that well, surface data, for example, water cut sampling, etc., pressures, upstream, downstream, choke parameter. If that's inappropriate sampling points, we don't have any temperature, pressure from the Christmas tree or valves in the facilities or in the pipelines. So these kind of examples and guidelines to us when we need to consider any proper data we need to collect from the field. And should be considered very well in the early stage of the field life when we designing the essential points and essential parts of this production system, and when we have to consider the future well monitoring. So as monitoring basics and daily basis monitoring, production history. So production history, for example, you can see what the well is doing. So this is very important part of any well performance monitoring. So if we have a missing data and we don't know actually what will happen, so what is the remedial action afterwards? It will be not easily predicted and not easily implemented. So recording well parameters at frequent intervals. So for example, is it per minute? Is it per day? Is it per hour? So each point is very important to us. So I think nowadays the technology give us a good shot of the recorded data when we have in our hand as end users. We can see each point when it happened and what time and what is the readings of those points we have recorded. So production rate, wellhead flowing pressure, for example, wellhead flowing temperature, water cut, and water chemistry from the labs when we have, as we said, proper sampling data, GOR, shut-in pressure, etc. So each point, it gives us and indicate where the problem is. If we have a problem, for example, if we're focusing on this part, we can do acidizing because we've suddenly seen a decrease in well production rate. So we think after monitoring the performance of the well, we think this is the remedial action we need to take and see whether there is a good indicate of this acidizing helping the well going back again to its original production rate. Recording well parameters, for example, for instance, water cut and water chemistry. So taking this illustrate as an example, we have a certain injection wells, and those injection wells, it's injecting very well. So what happened to this poor water injector well? Why it's these kind of poor performance we have here other than the other wells? And what is the impact of those wells to the nearest wells? Why we have seen some wells have a good indication of receiving the pressure support and good production rate, and the other is not. So is there any communication between those wells? On the other hand, the production wells. So many production problems are because of water, maybe this is indication of the performance of this injection and the performance of those wells regarding the communication and the formation and what happened afterwards regarding the production rate. And maybe as we can see there's a highly water cut raises on those wells besides of the oil rate. So could be indication there is a need of take an action to reduce that water cut. So monitoring water cut as a total liquids from those wells and or seeing what's the type of fluid or water came to those wells. And when we do water chemistry, so what type of water injected on those wells, what we can see from the production, and what kind of water we have to inject to enhance the production rate for the wells in this area. So these kind of questions we have to consider in terms of monitoring the field performance and the wells performance as it injectors or as it producers. So having said that, water breakthrough maybe can be happened on the nearest wells or the farthest wells in type of what is the reservoir type, what is the reservoir characteristics, is there any channels between those wells, because we sometimes have seen there's a water breakthrough in some wells because it's very good injectors and very good producer, but there is a channel and maybe there is a good communication between those the injector and producer, and that causes there's a water breakthrough because some happen inside the wellbore. So these kind of recording well parameters very important, very essential to be considered, to be planned, to be implemented. And what is the cycle of taking readings? Is it, as having said that, is it by per minute, per day, per hour? What's the process we are going to use? What is the software, etc.? Is this essential or not? What's the impact of any data we have to be collected regarding the field monitoring and well monitoring, performance monitoring? So well testing, it's a kind of monitoring basis and monitoring basics for the field management. Well testing give us a good indication what is going on inside the reservoir and give us a good indication what is the well performance is doing, what is the well is doing in terms of performance. Is it poor performance? Is it good performance? Why there's a problem, if there is a problem, or is there anything can we to be considered after doing all these well testing? So build up and draw down test and pressure analysis tests. It's kind of the test. What's the requirement? Why we do those kind of tests in terms of field monitoring or well monitoring. So the question or the answers came after. So if we need to investigate damage extent and the depth of that damage, the drainage radius of the formation, where's the reservoir boundaries? Is there any frequent reading we need to take? What is the flowing pressure, flow rate of that well, the GR that well is producing, the water cut from this well, and the solids production with the fluid from the well or the field. So what's the important part of those? Is it all important to us to diagnose any problem in the well? So the other thing we need to consider maybe can help us give us a good indication the production logging. So for example, taking this illustration, when we have a PLT, we can see how much this well is producing as a water. Is there any water breaking through? what's the each formation or each perforation contributing to that production rate. So this is the, we consider the total flow rate, for example, is it 2-3 MBD? What is the what's our rate for that well? Is there any behind casing? Something we have behind casing. There's any cross flow. So any identification of cross flow in this well, we can have it regarding this production logging. Is there any mechanical condition of the wellbore we need to focus on, and maybe there is a leakage in the casing or somewhere here inside the wellbore? We need to take action. Otherwise, this problem will be bigger and bigger. So, and the other parts of field monitoring and well monitoring is we can take it from the production logging. It's the fluid movement inside the wellbore. What type of fluid? What is the densities? What is the hold-up factor? We know the hold-up factor, very important part regarding the monitoring the well performance and the calculation of the flow rate, and what is the type of flow regime inside the wellbore. We can consider it from the production logging, and which zone contributed more than the others, and why. So these regarding the reservoir performance. So why is this interval just giving us 10 barrel per day, and this perforation maybe can give us thousands of barrel per day? So is there any problem with the permeability? Is there any scale? These kind of question, we can have it from the fluid entries and fluid sampling, and do the lab investigation regarding this. So this is very useful for matching models, our software models, to calculate what is the actual flow rate after we do the matching points. So we can get accurate flow rate for each part of the interval, and for the total flow rate for the whole wellbore. The other things we can consider from production logging is the cement condition. So if we have any cross flow, if we have leak detection, so we can know immediately is there any problem with the cement, how we can do any plan to overcome this problem. Otherwise, we will have more water breakthrough, and that cause maybe a well die or unwanted amount of water in the facilities. So recognition of presence of formation damage, as mentioned. So any pay zone, is there any problem with this pay zone, for example, for instance? So why this pay zone don't give us any flow? So identify producing zones and any damage regarding this zone. It's very helpful to diagnose why this formation it's not producing. Is there any reservoir issue? This reservoir issue is responsible for low production rate from this formation. So how we can deal with that low production rate? What is the problem, and what is the sufficient remediation to overcome this insufficient pressure or maybe flow from this formation? So taking this consideration, we can think about the flow restrictions. So this flow restriction came from a couple of common problems in the wellbore or the reservoir. So scale, formation damage, sand formation solids, hydrates, wax, asphaltene, loss of tools in the well. Sometimes we do an intervention, survey or intervention, and we lose some tools inside the wells, and that cause we may be losing that production from that wells. Maybe that loss make mechanical damage or tubing or casing collapse, for instance. So these the major problems we can see from the field life. It's maybe happened in early life, maybe in mid or late life of the field or the well life cycle. So these kind of problems we will discuss today in our webinar. So wax and paraffin precipitation. What is the wax? It's a long, straight hydrocarbon chain molecule. It's a heavy liquid participate in the inside the wellbore or any part of the production system. It's not easy to handle. It's caused by decreasing in the temperature. So the wax molecule begins to solidify. So it's a major problem when we have a wax in our well or in the reservoir or the facilities. The temperature at which solidification begins is referred to a cloud point. So it's when the wax deposit appear. This is the first point when we have starting wax in our well. Melting that wax need a certain process by application of the heat. So wax and paraffin participation. So this is one photo of where we have wax inside our wellbore. So you can see how much it's affecting the production rate from the well. This causes back pressure on the well. Maybe the well is not producing much as possible, and afterwards it will lead to the well it's being lost of production, and the well is die because we don't have any remedial action when that wax appear, and how we can remove that wax from the inside of the well. So is it in tubing, in casing, in the flow line? We need to monitor these things is very carefully and very close. Otherwise, we can lose those wells. So the chemicals give to the lab and the results. It's very important to be considered and to be monitored very well when we have starting. For example, the production rate is going down, and why this going down? This kind of problem when we have considered the reservoir characteristics and the PVT and the chemistry of the reservoir, and we have, I think it could be there is a wax inside and there is evidence in the surface. So depends on fluids and temperature. There is crystals form at wax appearance temperature. So the transition temperature, when we have less temperature, we have increasing in the viscosity, and we have to think about what's the wax inhibitor and pour point represents, and we have to put insulation. What is the option to increase the flow rate? Is this because the wax we have low flow rate from those wells? So do we need a mechanical or any remedial action in terms of solvent, or we need to put we do a workover to remove this wax? We have to have a plan to remove this wax immediately from the well. Otherwise, you can see from this illustration with the big impact of the wax inside the wellbore. So it's almost taking the whole area in volume of the pipe. So do we need to put any heaters to remove this wax? Because increasing the temperature this they will cause by reducing the viscosity, and then we have nice flow rate. So this is what will happen. So this is what will happen inside the wellbore. There's a diffusion of wax inside the wellbore, and this wax will reduce the amount of flow rate. Having mentioned that the wax appearance temperature, it's called watt. So starting from this point, it's almost depending on the reservoir characteristics. When we study the PVT and reservoir parameters, we will know exactly when we could be the wax appearance temperature starting. So how we can increase the temperature, how we can take action before seeing a wax, or just starting from this point, this stage, before this problem increase, and plugging all the fluid flow from the reservoir to the surface. So how we can remove this wax and rid of this problem. Asphaltene. So the other problem we have to consider, the asphaltene. So asphaltene, it's kind of material insoluble inside the wellbore, inside the reservoir maybe. So it's heavy aromatics. It's a very big problem to us when we have asphaltene. So this a problem. There's a chain of aromatics, resins, and aromatics. So it's very important to know when we have asphaltene, when we have evidence of asphaltene. Is there any change in the pressure or temperature inside the well, inside the reservoir? Why we have seen some asphaltene in our production? The removal of this asphaltene is very difficult, because we need to mill or reperforation, maybe any solvent, and this solvent, it's not take action removing this asphaltene just immediately. It will take time, and this taking time may costing more money and costing more time from the production of the well. Is there any squeeze treatment we need to do? Either we have do a squeeze, maybe it's not successful from the first time. So asphaltene a big problem to us when we have like this kind of problem inside the wellbore. So it could be in the early field life. So in the early field life, we can see it in the surface, because we have a good reservoir, we have a good properties of the reservoir, good condition inside the wellbore, but it's just participation in the surface facilities. So it could be in the choke and the flow line. So we can see asphaltene. Somehow we can see it inside the wellbore when we have a later field life, or not a later field life, or we've seen it in the surface, but we didn't take any action, and this become inside the wellbore, and the problem is more difficult to be deal with, and this need a mechanical or any other remedial action, and the problems become more worse when we don't take any action, and this lead to the reservoir itself. So the deposition point reaches the reservoir. We have a major problem now. So why we reach this point? Because we don't have any active field monitoring program, and the field management is very poor, and we have more problem reaching the reservoir and all the system of production. is very big problem to us when we have asphaltene. So what we can do, how we can remove this asphaltene precipitate inside the wellbore or inside the reservoir itself. We have to consider a plan to remove that asphaltene. So the asphaltene remediation, it's operation maybe, operation change, reduce bottom hole effluent pressure. Maybe it could be help to remove that asphaltene, or pigging in the for the surface facilities, for the flow line. If we have asphaltene and flow line, a cold tubing, we can do a cold tubing and to lifting or injecting any polymer or solvent to remove this asphaltene from the wellbore. Wireline cutting, maybe you can run a gauge cutter, remove this asphaltene, which is precipitated into the wellbore, inside the wellbore. We can do a chemical action to remediate this asphaltene by periodic aromatic flushing, xylene, for example, for instance, common use for production tubing deposits. So this xylene, it's a common way to use. Inhibitors or dispersions injection in producing tubing. So injection these inhibitors to inhibit the asphaltene to participate inside the wellbore or the surface facilities can help us remove this asphaltene from the production system, or squeezing or using a gas lift to remove this asphaltene. So it's any kind of remedial action need to be considered, need to be addressed very well, need to be studied, and why we need to take these remediation actions regarding of the reservoir properties. So some remedial action become worse and worse because we don't just choosing one of them without considering the other parameters for the reading of this asphaltene problem. Scale. So the other one is oil field scale. So what is scale? Why does it form? The types of scale commonly seen in wells, the cost of downhole scale, where does it form, and how do we control scale? You know, the scale is very important problem we facing always in our wells. It's a more common problem in the wells and the field. We can see it even in life, in our house. So not just in the field, but whereas we're talking about our wells and our fields, we've seen a lot of scale problem inside the wells. So scale is any organic solid material that participates in the reservoir, wellbore, or topside equipment during or oil and gas or water production or related operations. So this is the very simple identification of scale, brief identification of scale. What is a scale? So deposition of mineral scale independent of number of variables. So how the scale deposit inside our wells? And the first factor is changing in pressure. So changing pressure somehow leading to deposit of the scale inside the wellbore, inside the reservoir, inside the facilities, surface facilities. We've seen a couple of examples of the scale. Temperature changing, you know, changing from summer to winter for a day and night. Maybe from the bottom of the reservoir to the surface. These kind of changing temperature phenomena can maybe kind of helping the scale to deposit. And degree of agitation during formation of crystals. So some crystals formed in the end of scale deposition. The size and number of these crystals, maybe it's big enough to deposit inside the wellbore or the reservoir or the facilities. Impurities, when we have, so for example, have we seen the illustration before? when we have very close injectors, and the water injected inside those injectors is not fine enough. There's a lot of impurities inside it, and we can see it in the other hand from the at the end in the produced wells. This caused by it will cause in the end by scale deposition inside the wellbore or the reservoir. So we need to consider these factors very well. We need to have a close focusing on it, and what kind of and what type of water injected or fluid injected inside our wells. When any do remedial action for any well, what type of chemicals we are going to use. Otherwise, we can maybe by side effect causing scale deposition. So scale deposition normally manifests itself as rate reduction. So why rate reduction? As we suggesting this take a part of the whole volume of the flow regime inside the wellbore. So it's reducing the volume of it, and then we can see in the well performance parameters there's a reduction in pressures and temperature in flow rate, and noticing that maybe in couple of days or maybe this caused by a long period of time. So there is a certain decline in the production rate. We need to investigate why we have like this reduce in the production. So what is the cause of this production become decreased? And some of the problems is deposition of the scale. So what we have to be considered, change in water cut, if there are any change on water cut, and we have to do a lab chemist to indication of the scale. So concentration in milligram per liter. So these parameters can play a good role in deposition of the scale. So these examples of fields around the globe. So you can see the parameters which cause when we have a fluid compatibilities, and maybe there's an incompatible water, seawater and formation water when you have injecting and any kind of fluid inside our wells, and this cause scale deposition inside our wells. So we have to be very careful when using seawater as a kill fluid. Type of scale: carbonates, sulfates, iron scales, other scales, for example, sands, clays, fines. So these kind of scales, we can see all of it, some of it. It depends on what type of fluid inside our wells, inside our reservoirs, what we have used as injection, water injection, gas injection, what is the reservoir characteristics and parameters, what is the water lab can tell us about each type of scale formed inside our wells. So calcium carbonate, we've seen it a lot in daily basis in our house. So this calcium carbonate, and we can see it just not in the field, in other places. So it's very famous, very common. So how it's formed by water and CO2, we can have it. So producing wells, we can have a water breakthrough. So this water breakthrough inside our wells can form a scale, and this scale deposit inside the wellbore. So how we can take a reaction? It's concentration of calcium and produce water, pressure, temperature, these kind of factors playing heavily in deposition of the scale inside the wellbore. often first seen maybe at pressure drops. When we have it drops outside the well, when we have in the choke or in the flow line bends, maybe in some valves, in the gate valves in the surface. So we can see some kind of indication. We have a scale from these parts, and we can have indication maybe the scale is already deposited inside the wellbore. So we have to take an action. Sulfates, the other part, another thing of the scale. So formation and that seawater can make any other type of incompatible when we have it together inside the formation. So this kind of scale formation inside the wellbore or in the formation containing from the incompatibility of the water, seawater and the formation water. So water samples taken at surface represent the average water chemistry, which can misrepresent. So not we have to take this in our mind. It's not the actual represent of the surface or present the scale inside the wellbore. So we have to it's not the scale potential. We need to know which zones producing and where this come from and where is participate deposit inside the wellbore and what is the effect in our production. So is it the real data? We need to investigate more to know exactly how that affects our production. So it depends. So it depends on ratio of formation, producing water, and concentration of barium and sulfate. We need to study it well from the lab chemistry. So these kind of investigation and know exactly what is the percentage and where is precipitated and when deposited, if it's in highly permeable streaks, so that cause losing a large amount of production from that reservoir, that formation, that perforation, when we have a mixture and we have a water breakthrough, and if we have seawater, for example, so this may be form a scale inside the wellbore and plugging all the perforation or some of it, and we have a scale not just inside the perforation, maybe inside the wellbore itself or the surface, or maybe inside the tubing, production tubing. So we need to investigate when we have any kind of identification. There is a scale inside our system or inside our well, to how to remove this scale. What is the scale parameters? I mean the chemistry of this scale, and what is the best action we need to take? What is the best solvent or mechanical or operational action to have to remove this scale? Temperature and pressure. So temperature and pressure, a major factor in scale deposition. So carbonate is less soluble as it less soluble with increasing temperature and reducing pressure. So we have maybe this carbonate because increasing temperature and the pressure is decreasing. Sulfates tend to be more soluble with increasing temperature and pressure, less of an effect. So this kind of scale we can have seen in where we have a difference in temperature and pressure in inside the wellbore or inside the surface facilities, and when it can be happened. So we can think about carbonate or sulfate regarding these. So these kind of factors playing the general roles in scale deposition. Health and safety. We know scale maybe have some radiation. So these clays and deposition inside the wellbore need to be very careful. We need to study it well, do the lab water chemistry to know exactly if there are any kind of radiation inside, because it's emits alpha and beta and gamma radiation, and it's generally unsafe for human being. So we need to diagnose further if there are any kind of radiation inside. So before handle these kind of scale, we need to give a permit if it's required to if and the following this permits following the regulation of that country, and sample must be properly packed to ensure contaminated during shipping to handling facility very safe. So the health and safety issue is very important regarding this. So when you can see it's in downhole safety valve, Christmas tree, pressure relief valves, control system, separator, etc. So these places we can see the any type of radiation investigation. So we can check by these parts. It's as a further investigation of any radiation from this scale before do any action. So between 2004, 20% of North Sea operation well maintenance costs related to scale problems. So 80% scale inhibition and removal. So you can consider how much we spend in scale inhibition and removal. So take a big consideration and part of the problem of inside the wellbore and field production. So this production lost about net well maybe 25 MBD per day, 1,000 barrel per day. So it's a big amount of loss regarding the scale. So what is the downtime regarding this scale control and removing? And what is the removal criteria we followed to remediate this scale deposition inside our wells? And the other factor, as we said, safety and environment consideration. So there is a big impact because that scale in our field and our wells. We have taking another example from the other fields around the globe. So we've seen, for example, in Colombia, significant volumes of mud are lost. The mud contains large quantities of calcium carbonate on water breakthrough less than 1%. It's a scale. So we have a scale seen, and maybe because of scene, we do a side track, and we losing this well, and we have to consider a side track and leaving that well away, because the remedial action, it will cost more than if we do a side track to the well. So we have facing some example when we have a large amount of scale, and the cost of it is very large. So it's enough money to do a side track. Otherwise, we can spend much money on just remedial action to remove this scale, with the outcome of that remedial action, it's not worth enough. Where does scale form? The inside of production separator is supposed to look like this. So you can see it's very nice, clean picture of inside what we have inside the separator. But the real situation is this. So if we go back, you can see the space inside the separator. But after we have this situation, so the difficulties of handling the amount we need from the produced wells, it's become less and less, and we can lose a huge amount of production rates because this ineffective scale control. So how we can remove this scale, we need to consider it very well and put plan beforehand to remove any scale deposition inside our system. Otherwise, we have to face like this problem. So is it possible to remove this scale or just remove or put another separator instead of this separator? So what is the best choice for us? You have to consider this. So for instance, the sunscreen, it should be looking like this, but in reality, it's almost plugged because of scale. So the scale deposition inside the sunscreen make the sunscreen less effective, and how you can consider how the fluid can pass through this sunscreen. So if you are looking up about the scale, so steel production declines and a scaling environment, it must be scale and insufficient data. So the data is very important part here, because otherwise you cannot identify if it's a scale or not. What is the problem? Is it very worse, or is in the first stage, or the mid stage, or late stage? How we can remediate this if we have wrong prognosis and we have a wrong decision made regarding this insufficient data. So we have to always ensure data is analyzed fully. So how we always ensure data is analyzed fully: accurate water chemistry analysis and scale prediction, the analysis of solid samples. When we have receiving these samples, we do a good investigation about the parameters and the percentage of these solids recovered from the well interventions. So well interventions, it's very important to collect an accurate data regarding those wells, because it's a lesson learned to us after this well intervention to prevent this scale deposition in the other wells. So it's proactive work. So well performance modeling, the other part of recording the right data and putting and matching the right data, and we have an accurate well performance afterwards when we incorporate relative permeability effectiveness of effects and as we said, the production logging or flow test doing in for specific wells, if we considering there's any problem regarding the well performance. So how do we manage barium scale? We have to prevent mixing incompatible water, low barium chemical emission with cation, downhole, topsides, dividing point between high and low. How we can, because if we have a high barium or low barium, so somewhere between 50 and 250 ppm, depends. We have other factors playing around. We have to consider it beforehand, do any remedial action. So what is the remedial action? It will be maybe chemical dissolution, mechanical removal, or side tracks. So this remedial action, it came after what we have already done to remove this scale. So continuous injection via chemical injection control line, and continuous injection via gas lift, or atomization and junking issues. So junking refers to the undesirable accumulation of deposits such as wax or asphaltene. Atomization refers to the process of breaking down a liquid into tiny droplets or particles, often in the form of mist or spray. So we have to consider when we need to our deployment will be, it's above a packer or below the packer. So if it's above the packer, we need to know the hydrostatic pressure of fluid in line with wellbore pressure. So we don't need a pump cavitation, so we have to consider this. Most applicable to prevent CaSO3 deposition in upper completions. So how we can do it if we consider pumping upper the packer, unless we have to design in the proper way and put away any restriction inside the wellbore. So where the injection line blockage, for example. If we deployments below the packer, so matrix contained scale inhibitor. So it's integrated fracture prevent, limited volume of inhibitor can be incorporated into the proper material. Integrated scale inhibitor may be spent before inhibition is required. Impregnated propellant is expensive, so it's an expensive way. So it's most cost effective. So we have to consider which type of inhibitor need to employ deployment. It's below the packer or above the packer. So we need to have beforehand what's the proper way, and we need to consider the other factors of the well parameter and reservoir parameter. So the treatment of scale inhibitor squeeze, bullheading, flush, and main treatment on overflush. So, for instance, bullheading chemicals pumped directly down in rate 3 to 30 ppm. So, stage 1, pre-flush. Stage 2, pump and scale inhibitor, and pump overflush. And stage 4 is shut-in and return the well to production. So, what is the sequence of our process, and what is the sequence of our remedial action, where to pump and how much we need to pump, and what is the speed of pumping, what is the volume, where we have to pump, which formation, which perforation, do we need any extra materials and extra solvents to pump, the direction of this pumping fluid, do we need any extra gel direction? So we have to put our plan very carefully. Otherwise, the well cannot be on production again, or we don't have the accurate fluid after do our treatments. So in scale inhibitor squeeze treatment issues, significant risk of formation damage. So this is one kind of problem we're facing after doing the scale inhibitors. So we do a formation damage. Pumping and not accurate rate, or just pumping in very fast or very low may cause formation damage. The diversion agents of treatments maybe don't reach the desired layers and may cause a reservoir damage or layer damage. This is not actual the wanted treated zones. So if not, is the well still at risk from scale? So these kind of treatment issues we need to consider. So how we can do that? Calculating bottom-out temperature, rate, using the proper software, and high rate squeezing. It's calculating the fracture pressure versus temperature, reservoir pressure. So it's regarding the rock mechanical studies. So we have to study it very well before doing any remedial action to remove that scale. So high rate squeezing or low rate squeezing, how we can know that? We have to calculate the surface fracture pressure versus rate using Prosper or Wellcat. So the hydrostatic calculation is very important. The step 4 always include an operation safety factor of at least 500 psi. So this is, I think, a typical value for safety factor. before doing any remedial action and removing the scale from the wellbore. So scale inhibitor deployment issue at the reservoir pressure. So injecting any inhibitor may be causing less reservoir pressure. Large amounts of inhibitor will be inside the wellbore or the reservoir and causing less permeability, less porosity, less more problem for the rock parameters. Maybe will direct the problem, will change the problem from, or the normal issue of the reservoir may, I mean, from wet, oil wet to water wet, or otherwise, or in the reverse. So this kind of problem when we have scale inhibitor. So several conditions can be put in place to assist well restart. So overflush, medium, oil and diesel, maybe using cold tubing, high gyro oil fluids, we have to consider it very well because the mixture maybe still we have CO2 and H2O, and then we have another scale deposition and gas spiking. And this spike may cause a wellbore damage inside our well. So for natural wells, tubing and overflush volume can be gas spiked during squeeze. So these operations benefits include eliminate diesel displacement. So using diesel displacement, maybe we have less amount of OPEX spent to these kind of remedial actions, and maybe this cause a faster well recovery because we have less a reduction in deferred production losses. Large treatment can be pumped, longer squeeze treatment lifetimes. So these scale inhibitors deployment issue. The scale control in general, once scale form, they can be difficult to remove. So this is the we have to put in mind. So we need to do any action before we have a scale deposition inside our wellbore or inside our facilities. So when we have it, it's not easy to remove and to handle. So the two methods are in common: the mechanical removal and dissolution. So we can use acid and some chemicals to remove this scale, or just we do in term of mechanical, we can do a milling. Methane anhydrates, these other problems we can face inside our wellbores. You can see from the illustrates how big is it, and how this crystalline solids composed in water of gas molecules. So we have a plug regarding the hydrates. This causes significant reduction in our production rate. There is a safety issue associated with remediation. So how we can remove the hydrates. The hydrates may become formed in tubing and in downhole safety valve. When it's opened, we can see some kind of hydrates. So considerable concern about possible sudden movement of the plug. Maybe when we have a plug and can maybe damage to the tree and downhole stream valve. So have you seen? It's a big one. So when it's moved, maybe can have a damage inside our wellbore. So what we can do, maybe you can some solvents related to molecular weights. We have to calculate very well to know what exactly we need to put inside our well. So we have a certain study, the typical hydrate distortion curve. So dissociation curve. So this curve can tell us what is the solvents we need to use and when and why. So this hydrate blockage remediation, maybe this depressurization, chemical treatment, or thermal method or chemical methods. So it's regarding what we need and what we have in our system. So the most commonly used method is reduction in system pressure below the hydrate pressure at ambient temperature. So this curve can tell us when we have to reduce the pressure and why and where we have inside this curve. So it depends on what is the stage of forming this hydrates. So we can play with the pressure to remove this hydrates. So moving from this part to this part. It can be relatively quick and effective. Most inhibitors can remove, most inhibitors use metal or glycol to blockage. This is not always possible. So why it's not always possible? Because having said that, it depends on the well parameters and the reservoir characteristics and why we using, what is the volume of all any of it, and why we use it, because it's play a major factor on removing this blockage of the hydrate. So cold tubing, jet pumping, or circulation of hot oil down annulus into the wellbore, maybe in or the flow lines, or where we have hydrates, can maybe remove the hydrates and we have no hydrates. The other problem, hydrogen sulfate. So it's very important problem and very dangerous one, because there's many death issues and death problems happen because of that H2S. So it's potentially poisonous and can be potentially harm for a human being. So we need to take care when we have this formed H2S inside our wellbore. So produced water and sulfate reducing bacteria generally lead to H2S. So maybe the produced water or any bacteria inside our wellbore may be producing H2S. This need to be taken when we have any action to remove that H2S. So incompatible of injected seawater and between the transition we have forming this H2S, and we can see it in producers. This H2S can be very harmful to the inside the wellbore. I mean the chemicals, the mechanical issues we have seen because of this. So need to consider the completion of the wellbore, because these formation may be producing H2S. So a remarkable consideration for the completion and what type of casing and tubing need to be installed inside the wellbore. The final one, the corrosion. So we have corrosion issue everywhere. So if we take the wellbore, one of an example, so maybe we have any part of well completion there is exposed to the corrosion when we have a water breakthrough, and we have corrosion regarding a very fast flow speed, and we have erosion, and then we have corrosion. So for example, for instance, when we have a breakthrough, when we have any type of intervention happen to that well, for example, if we maybe run a multi-fingered caliper in one hand or another, we can see there's a scratching inside the casing. This scratch starting to be a punch inside the casing, because when maybe we have some chemicals or helping to puncture those and casing inside and from the inside, from the outside to the inside, and we have a water breakthrough, and we have corrosion in the whole casing or tubing. So corrosion, it's very important. We have to do a corrosion management very carefully, and study the materials used in well completion and surface facilities. Otherwise, we can see corrosion inside our wells and our facilities. So what caused corrosion? CO2, solids from the erosion, acids when we do any acid jobs, or there's a reaction inside the wellbore, and these acids cause this type of corrosion. And completion intervention, as mentioned, oxygen, microbiologically induced corrosion, microbiologically induced corrosion. So, and as H2S has mentioned that. So we have to take careful of our wells. Sometimes we don't see the corrosion inside. So this is the internal part. So when we remove the external part, this is a cutting. So you can see it's very clean from the outside, but from the inside, it's very rusty, and the corrosion is very clear to be noticed. So when you have to consider any corrosion, so the corrosion engineer need to be to study it very well. Otherwise, it will punch in all of it, or maybe it will be maybe lost because their reduction rate and other problem. Maybe it's a gas well, we have producing gas, and there is a big problem because of that gas or any fluid harmful to human or the environment. So we need to do the corrosion management beforehand to ensure the well integrity and well integrity of the facilities regarding the corrosion issue. So we can do a multi-finger caliper, downhole video, or ultrasonic imaging to know where exactly we have problem inside the wellbore. And this identification help us a lot to remove this corrosion issue and the problem, and how we can remediate these issues. So this is the end of the webinar. I'm very sorry if it's more than 1 hour, takes a long time. Thank you for attending, and if you have any question.
You hear me? Hello. Thank you, Engineer Mohammed, for this amazing webinar. It was fruitful and full of information. Now it's time to take a break for 2 minutes, just to fill in the feedback form that I will send in the chat box right now. And then we will start receiving the attendees' question for the Q&A part.
Okay.
So I've just sent the link of the feedback on the chat. You can save the link later to fill it, and now you can start sending your questions. Okay, so it's time to receive your questions. So I have a private question from Patrick Kempasa. He is asking how to know sulfates or carbonates are inside the well by wireline logging or tests or by just seeing.
Say it again, please. What
Okay,
you need to know?
1 minute. How to know sulfates or carbonates are inside the well?
Sulfates or carbonates is more regarding the water chemistry. So you need to investigate when some it's maybe coincidental. We have seen any evidence of one of it or both of it. We can do another investigation, see if it's an early stage or mid stage or late stage. Most of the cases when we have a repeat monitoring for our wells, when we have any reduction in parameters and well parameters, we need to do extra investigation. So the first thing we need to do is to do the well parameters investigation. I mean, well parameters upstream, downstream pressure and temperature, taking the water samples and analyze in experienced people analyzing the chlorides and fingerprints of any kind of sulfate or carbonate inside our oil bore. So you can see it in the surface facilities or inside our bore. If it's inside, we have to do any wireline jobs to take for example, fingerprint from the wellbore to know if you have scale or not, or carbonate inside your deposit inside the wellbore.
Okay, thank you. The next question from Wendy. What is the difference between water cut and water hold up?
Water hold up, it's a parameter calculated from the when we have production logging. And the water cut, it's a water sample taken from inside the wellbore or from the surface. There is a sampling point. You can take a water cut sample to know exactly what's the water percentage that well it's producing. So there is difference between the two. So the hold up is calculated to monitor the well performance, well flow regime, and how we can do the well performance analysis and improve that performance of that well.
Okay, thank you. The next question from Engineer Ahmed Chamari. He was asking about the reservoir monitoring part. Was that in the beginning or?
Reservoir monitoring is just you should put everything beforehand when you do when you need to develop any field and when you start producing from that field, you should do a surveillance plan for that field and for that formation beforehand. So what kind of data you need to collect and what is the period of collection of these data. So some data it's as a daily basis. For instance, the wellhead parameters should be daily basis. So and the others could be every 3 months, every 6 months. So it's annual data or seasonal data. When you need to take it, it's the day or at night, because there's a difference in ambient temperature. So there's a certain process for each data to be collected. So it's not can be collected randomly. Otherwise, it's all the data will be missed and insufficient data. Having said that, in our webinar, so it's very important to know what type of data and when to take it. So for the reservoir, of course, on every single point in the reservoir, I mean the wells, facilities, starting from the first beginning of production.
Okay, thank you. Another question. When is the correct time of the project for implementing strategies to prevent wax and scales in our wells?
You have to know your reservoir characteristics. So you are going to do a field development plan for this field to produce from it. So you need to know the PVT of this field. You need to know which formation you are going to deplete it, how many wells, and what is the reservoir targeted, and what is the characteristics of that reservoir. Otherwise, you cannot manage it very well. So after you have a management plan, so you can say you have a very handy, powerful monitoring process.
Okay, thank you. Another question. What causes high water cuts and fast pressure depletion in gas condensates well?
I'm not sure about the answer, but high water cuts, it's related for the gas wells, any chemical reaction between the gas, maybe you have impurities, so caused corrosion and somehow inside the wellbore, and there is a wet water breakthrough inside, so that will cause the problem to be increased, and this caused immediate reaction to remove that water breakthrough from that exact well. So you have to consider each parameter before do any reaction. What I mean by parameter, so you have all the data in hand. I mean the reservoir parameter and the well parameter. You have an intervention history for that well before do any action.
Okay, thank you. So another one is asking, what can we do to liquid loading remedial in retrograde gas well producers?
What's the last part?
What can we do to liquid loading remedial in retrograde gas well producers?
I'm not sure, because I did not face something like this problem before. So I'm not sure about the right answer. So he have to consider the reservoir engineers before do any type of remedial action.
Okay, thank you. I think another two questions left.
Okay.
So, how can you overcome the limitation of well production logging in unconventional reservoir?
Unconventional reservoir is very difficult to produce from it. So they have heavy liquids. So there's a certain companies around the globe working on it, and it's cost effective. They spend more money to produce those type of fields. because need a certain technology. So there is a certain technology for each field, because having said that, each field has its own characteristics. For example, for instance, if there is more gas, less gas, it's heavy viscous fluid inside the well. What type of do you need a gas injection or polymer injection? Do you need any heat exchangers to use for your facilities or inside the wellbore? What type of enhanced oil recovery procedure to follow? So each one has its own. So there's no right straight answer for his question.
Okay. So Ahmed is asking, what is the way to get rid of wax entry pipeline?
One of the ways they use pigging to remove this wax from the the pipelines. So running these pigs inside it and remove all that. Or yeah, they use heaters for certain spaces in for the wax deposition. If it's repeated deposit of wax. Now, if that well, it's repeated depositing wax inside the flow line. So there is heaters installed for a certain calculated space, and it will reduce the melted wax inside the pipelines.
Okay, thank you. For the last question, what is the best way to calculate methanol and glycol rate to prevent hydrate blocks?
You know, the surface companies using their own softwares. I'm not sure. I didn't do it before, so I'm not actually how they calculated it. But there is a certain software that they are using, and there is certain formulas for that. Nowadays, there is a certain software to calculate the required amounts to be injected as inhibitors. And it all depends what is the percentage of the problem they have. So you need to know how much to inject before injecting in the wellbore or in the facilities, service facilities.
Okay, thank you. I think this is all for today. Thank you, Engineer Muhammad, for this fruitful webinar. And I'm sure that everyone benefited from it. And thanks all for attending this webinar. Please note that the certificates will be sent within 1 week from today. Thank you for attending, and see you soon in our next webinar.
Thank you very much. Thank you all for attending this webinar, and hopefully it's have a good impact on your knowledge and gets most of it. Thank you very much.
Thank you.
Bye-bye.